Alright, now I'm going to do problem 81. In 81, we have a merry-go-round, which is one of those things you find in playgrounds. It's a turntable, but it has these bars on it here, and it can spin around. And kids hold on to it. It's really fun. One of my favorite things when I was young. Alright, this has a 3-meter diameter, so the radius is equal to 1.5 meters. And it has a mass of 250 kilograms. Okay, and it's initially spinning at 20 revolutions per minute. Okay, then John runs over here, jumps onto it, and he's running at a velocity equal to 5.0 meters per second. And he runs tangent to it. That's key. That means that angle is a 90-degree angle. And John has a mass of 30 kilograms. And we want to find out what is the angular velocity final in RPMs after John jumps on. Alright. So again, we're going to do conservation of angular momentum. In this case, the merry-go-round is already spinning, so it has its own angular momentum. This is the I of the merry-go-round. We're going to call that I of m times omega initial. That's its angular momentum. Plus, John has angular momentum as a point source. So he's going to come running in. That's the mass of John times his velocity times the radius, how far he is from the rotation point, which is the radius of the object. That's his angular momentum times the sine of the angle, but we know it's already 90, so it's going to be equal to 1. Now at the end, he jumps on and grabs onto this. So what we're going to have is I, but we're going to have I of the merry-go-round plus the I of John, the moment of inertia of John, times the omega final. And we're going to solve this for omega final. So I'm going to just solve it for omega final right now. Omega final is going to be I plus mjv times r over the I of the merry-go-round plus the I of John, the moment of inertia of John. Now we got to plug in all those things because they're going to be different. So we know this is 1/2 the mass of the merry-go-round times its radius squared. That is I of the merry-go-round times omega initial plus the mass of John times his velocity times the radius over 1/2 the mass of the merry-go-round times the radius squared plus John, but John's a point source, so that's just the mass of John times its radius squared. Alright, now there's no r squared up here, but so the simplest thing to do is you could just take an r out, or you could just plug in all the numbers. It doesn't matter at this point because we have all these numbers, but you could simplify this more if you wanted to. I'm just going to plug all the numbers in. So I'm going to say this is 1/2 of 250 times 1.5 squared. Now before I do this, I got to convert 20 revolutions per minute into radians per second. So I divide by 60 and multiply by 2 pi. And I get that 20 revolutions per minute is equal to 2.09 radians per second. So this becomes 2.09 plus the mass of John, which is 30, times his velocity of 5, times the radius, which is 1.5, because he grabs on the outer edge. All that over 1/2 of 250 times 1.5 squared, plus the mass of John, which is 30 times 1.5 squared. And you plug all that in, and you're going to get omega final is equal to 2.33 radians per second. And once we convert that, we get this is equal to 22.3 revolutions per minute. So John running in, jumping on, sped up the merry-go-round. If he was going slower than the outer edge of it, he would actually slow it down by running on and grabbing onto it. But his angular momentum actually adds to the angular momentum of the disc already, and so it's going to increase it. If he was running the opposite direction, then it would be going the opposite way. It would slow it down. This would be subtracting his angular momentum. But they specifically said that the angular momentum was going in the same direction, or he was running in the same direction that it was spinning, so it adds to it. That's how you do number 81.